Let's do this example. We have a piece of elastic, we're told the length of it, and we're told how much it's extended by. Now you might recall in the equations we were talking about, we don't actually care how long the piece of elastic is, we're going to be modelling this like a spring, but we do care about its extension, delta x. So they've given us a piece of information that we don't need here. We're told that there's a mass of 0.050 kilograms hung on it. So we've got our piece of elastic here, we've got a mass, so we know the force that's acting here is going to be mg. We're assuming that piece of elastic has no mass, and the force is going to be the force due to gravity pulling that mass down that's therefore pulling on that elastic. Oh, well that's nice. The first question says, what force does the mass exert on the elastic? So that's Fg. So that's going to be mass of that mass, that sounds funny, times g. Okay, so we've got the magnitude and the unit. They've specified it for this question for some reason. How much work is done in extending the elastic? In this example, the work done is causing a change in the spring potential energy. So work is going to increase the spring potential energy, which equals a half k delta x, all squared. Problem is we don't currently have k, but we can use the force at this particular extension to be able to determine that. So the force in that example was mg, and that's got to be equal to k delta x, because it was in equilibrium. So we're just using this to determine the value of k. So k is going to be the value of mg we previously calculated, and for that force, the particular extension was 0.040. So that gives us the value of k of 12.25. We're not going to round it because we need this value later on. And the units are newtons per metre. So, to continue on with that elastic potential energy that we spoke about, we've got a half times the value of k times this particular extension was 0.040. Can't forget to square it. Okay, so to 2 sig figs, let's pop that down. Alrighty, we asked for the magnitude and the unit, so 9.8 by 10 to the negative 3 joules here. Next one, the student pulls the mass downwards through a further 0.04 metres. How much work does the student do? So we need to break this situation up. We have the piece of elastic and the mass, and that mass was stretching the elastic to a particular point. So imagine we haven't actually let the mass apply force yet. Once we've actually hooked it on and let go, we've had a change in the length, and that's work done due to the mass. If we have someone's hand come along and they pull the mass down even further, then there's going to be another extension here, which we're told is 0.04 metres. So one way we could do this is we could determine the work done to go from here to here, and we could subtract the work done that we previously did. You might do it a slightly different way, but this should get us the right answer. So work done in this situation, again, is going to be equal to the spring potential energy, half k delta x squared. You could do the subtraction at this point, or you could do it afterwards. So if I wanted to do that, half times the k we had before, times that total extension now is 0.08 squared. And if I pop that in, I get this many joules. Just double checking. Yep. So that means, therefore, work done by student it equals that 0.0392 minus the work done by the mass itself. So to 2 sig figs, that is 0.029. The next question is one of my favourites in this topic. So let's look at this now. We've got a storeroom. In a storeroom, a small box of 30 kilos is loaded onto a slide. Here's the slide. From the second floor, it slides from rest, so it's starting at rest here. Just going to put a line that one, to the ground floor below, as shown. Well, it should say to the side. The slide has a linear length of 6 metres, so this length along here, 6 metres. And it's designed to provide a constant friction force of 50 newtons on the box. The box reaches the end of the slide with a speed of 8 metres per second. We asked a very broad question, it seems. What is the height h between the floors? Well, we need to use energy conversions here. So let's think about the kinds of energy this has at the top and the kinds of energy it has at the bottom. Thinking about our 4 kinds of energy: gravitational potential energy, kinetic energy, spring potential energy, and any work done due to friction. At the top, it's going to have gravitational potential energy because it is at a height, no kinetic energy because it's currently stationary, no spring potential energy, and friction hasn't had the opportunity to do any work yet. As it goes down the slide here, there are things that are happening. Number 1, it is gaining kinetic energy. So when it gets to the bottom here, it has gained kinetic energy. It's at the bottom here, so it has a height of 0, so it's got 0 gravitational potential energy. This is not a case where all of the gravitational potential energy is poured into the kinetic energy bucket though, because as we mentioned, there's friction along this slide here. So that means gravitational potential energy has not only been converted partially to kinetic energy, but it's also had to do work to push through that friction here. So we've had friction the whole way this slide was going. So that means some of that energy, again imagining those 4 cups. So like I said, that gravitational potential energy has been partly poured into the kinetic energy cup, and partly some of that energy has had to be used in work done against friction. So when we consider the total energy is going to be equal to whatever the gravitational potential energy is at the top. And at the bottom, we're talking this point here. We've not reached the spring yet. We're not considering spring potential energy. And as I said, no gravitational potential energy because we're at a height of 0. That means that gravitational potential energy has been completely converted into kinetic energy and some of that work done due to friction. How does that help us determine the height? So I'm going to call this point 1 and this one point 2. So the total energy at point 1 needs to equal the total energy at point 2. So at point 1, we said we only had gravitational potential energy, so we might as well put mgh, h referring to this height here. Talking about point 2, we said we had kinetic energy and work done due to friction. Kinetic energy is a half mv squared. And work done due to friction, we've got a force applied over this distance. So remember, the work done due to friction was equal to the force times the displacement. We only care about that linear length of the slide here. We can't cancel off m, which is annoying, but it's okay, we were given m before. There's a few ways you could go about this. You could substitute in all your values, or you could write h and then divide everything on that other side, so half mv squared plus fs divided by this m and g that we had over here, just to get h by itself. So let's substitute. Mass was 30. The velocity at the bottom was 8 meters per second. The force of friction was a constant 50 newtons, and it was 6 meters it was applied over. Remember, we can only use work equals Fs when we have a constant force that's doing work. M times G. Let's calculate. Alrighty, double check on your calculator, but I get a height to 2 sig figs of 4.3 meters. So we had some really nice energy conversions there. We are now told in the next bit that the box is sliding along a frictionless floor. My dog won't stop barking. Evie! Anyway, what that means is, at the bottom here, some of that energy is gone. That box, that work done due to friction, that's not helpful energy. So now that it's poured into this work done area, the box no longer contains that. That work was done to push it against the friction. We had to consider it at the bottom here because part of that gravitational potential energy was converted into it. So now that work done is unhelpful energy that the box itself no longer contains. As I said, it was that work done to push against that friction. So now the box itself only has this kinetic energy. It is sliding along a smooth, frictionless floor, so there's going to be no change in the kinetic energy here. It's going to maintain that kinetic energy until it reaches this spring. Again, we don't have gravitational potential energy here because we're not changing the height. When we get to this spring, the box is going to compress the spring. So it's going to start at its natural length, and then it's going to be all compressed up, and the box will be here. And at that point, the box will be stationary and the spring will be maximally compressed. So that means the kinetic energy is being converted to spring potential energy here. So we can have all of this kinetic energy converted to spring potential energy. We have no work done due to friction involved because we're on a smooth surface. So let's do that calculation. So we need to figure out how far the spring is compressed. And like I mentioned, we've got that kinetic energy, half mv squared, is being converted fully to the spring potential energy. You could write 0.2 and 0.3 if you wanted to label the points here. Let's get rid of those halves. We are interested in how far the spring is compressed. So that means we want to find delta x. So to be able to find that, we need to divide both sides by k. And we're going to have to take the square root. You might recall every time in physics we take a square root, you've got to think positive or negative. We're just interested in the change in length, so we'll just take the positive in this circumstance. Let's now substitute. Alrighty, double check this in your calculator, but I get 0.25 meters. Another wonderful example of energy conversions here.